Jonathan. So I'm delighted to welcome you to the Cafe University webinar series. These webinars are intended to be educational, and they cover a variety of climate and health topics that are sometimes presented by Cafe internal team members, and sometimes presented by visiting experts from anywhere across the world. And content can vary from data science related tutorials like we're going to see today to sometimes grant writing tools and tips or lectures on advanced topics in climate and health. And most webinars are made freely available on our Cafe YouTube site afterwards, including this webinar. We do plan to record, I believe, and make it available afterwards. So stay tuned in the next couple of weeks, hopefully, for us to get that posted if you want to rewatch. So today we're extremely fortunate to be joined by Jonathan Gilmour, who's one of our fantastic Cafe internal team members, who has expertise in data science, software engineering, and data communication and visualization. And today he's going to be giving us an intro to spatial data processing and visualization in Python. So as he's presenting, feel free to put any questions that you have in the chat, and we can interrupt Jonathan if there are critical clarifying questions that need to be asked along the way. Otherwise, we'll try to reserve some time at the end for a more extensive Q&A where we can potentially even unmute folks and allow them to talk to Jonathan directly. So thank you again for joining us today. I am going to hand it over to Jonathan. Take it away. Thanks for joining us, Jonathan.
Wonderful. Thanks so much, Rachel. It's great to be here. Hi, everybody. So glad that you're joining us. So I'll share my screen. You may have seen the title of this as Introduction to Processing and Visualizing Spatial Data Using Python and Data Wrapper. When I was getting ready for this, I realized that Data Wrapper doesn't have the same kind of spatial data visualization capability as I would like. So we're actually we're gonna get through the Python, and then we'll use Flourish, which is another no-code tool for data visualization if we can at the end. Both Flourish and Data Wrapper are great options for working with data and doing some really easy and effective data visualizations. So I'll get started. If you didn't grab the link in the chat, here is a QR code to the materials. Let us know if that's not working. I'll just leave this up for a little bit, and then I'll move on to the next. And we can drop that link in the chat as well. Thanks so much, Rachel, for sharing that. Okay, so why are we here today? So climate epidemiology studies often use maps to communicate patterns of exposure and outcomes across space. So what we're trying to do with these visualizations is link outcome data with weather and climate exposures to analyze associations. And you've undoubtedly seen maps used to communicate data. Any map is communicating data. A map is inherently a visualization of some form of data. Maps are wonderful, and they're also terrible because they skew our perspectives in interesting ways. And they're on the one hand one of the only tools that we can use. They're probably the most effective tool for presenting spatial data, because spatial data is best communicated spatially, perhaps most easily communicated spatially. But that does mean that, for example, if you're showing something by county or by country, you're trying to show a metric, you will bias the viewer towards larger entities on the map. And so this is something just to keep in mind when you're using map, and we'll go through some more background on how best to communicate and visualize data. So what we're here today to do is to learn some primary types of spatial data that we would encounter in climate epidemiology, import and process spatial data in Python, create effective maps for exploratory data analysis or publications in Python, and then also how we can link spatial data across types. So some background that we will assume here, some basic familiarity with Python coding, so syntax and objects and functions. We don't anticipate that you have prior experience with spatial data. We're going to go through common types of spatial data. Hopefully there's a Python notebook in the folder, and my goal is to use Google Collaboratory um, for this webinar, and hopefully you should have very little friction, if any at all, installing Python libraries. But we're here to troubleshoot with you if you do have any. Google Collaboratory does a great job, and at the beginning of the notebook, I have a script for installing all the Python libraries that we'll need. So some basics of spatial data. So type number one is vector data. So we use vector data to display points and lines and polygons, and sometimes associated information. And we focus on data from polygons to represent the boundaries of geographic areas. So, for example, you've probably seen health data represented using administrative geographic areas. Here in the US, we often do this at the county level. If you've seen global data visualizations of health data or other types of data, it's oftentimes at the country level. We can even get more granular and go and do some visualizations at the ZICTA, the zip code tabulation area, or the zip code level. And these different administrative boundary levels allow us to get really granular or zoom out and work at a resolution that is easier to comprehend. So this is a life expectancy map, and we're looking here. The United States is an interesting example for any types of spatial representation exercises, because we commonly think of the United States as the lower 48. But of course, there's Alaska and Hawaii and a number of territories. And so that in itself can be a challenge in how do we represent all of those if you're trying to make a really tight, pretty visualization, but you also want to ensure that you are representing all of the areas that you're hoping to show measures for. So next type of spatial data we're going to talk about is raster data. So raster data are grids of cells of equal size. These are pixels that we use to store values of spatially continuous phenomena. So we often report climate exposure over rasters. So if you think about a picture, a JPEG picture, this is also a raster, actually. It's composed of pixels, and each pixel has a value. And so we've all probably seen rasters that are showing some data. They're visualizing data. A JPEG picture is also a raster that is visualizing some form of data. Here, this is projecting future heat stress in Australia. So you're seeing at two different resolutions. This is more granular. This is more fine. A raster of showing this heat stress with each little pixel in the grid showing us a measure. So this processing and visualizing spatial data gets really exciting and also powerful when we combine raster and polygon data for climate epidemiology. So oftentimes we have exposures reported with rasters, and we have health outcomes that we have stored in administrative areas. So think counties or states or countries that are polygons. And to study associations between the two, uh, between exposures and outcomes, we can convert rasterized exposures to polygon levels. And so we'll do that today with Python. So another thing that is important to think about when we're talking about visualizing spatial data is projections. So when we're working with spatial objects, we're usually working in 2D space. So the computer that I'm using right now is a two-dimensional screen. If you print something out, if you print out a paper or you see something in a newspaper, it's probably 2D space. But we all know the Earth is in 3 dimensions. So this presents a challenge. We have to convert positions and distances between 3D to 2D. And you've probably seen various types of projections in maps that you come across. And sometimes you'll notice that maps seem a little skewed. You might see some common projections make it seem like North America is gigantic, or it's really stretched, or you see distortions in the way that different land masses appear. And of course, every map is uses a projection, and so we'll have some inaccuracies. So I love this. All projections produce distortion of the Earth's surface in some fashion and cannot simultaneously preserve all area, direction, shape, and distance properties. So here are some different map projection types for the lower 48. And you'll see they're very different. And this is really important to remember when we're both thinking about how to communicate spatial data, and then also when we're evaluating what pitfalls the projection type we're using might produce. So we use projections to convert 3D to 2D. Lots of different ways to do this, and there's quite a bit of literature out there on what are the best projections for different scenarios. If you're looking at, for example, one particular state, you'll probably find a projection that is best tailored to showing spatial data for that state. So pick a projection that's tailored to the region that you're working with. You don't need a projection that is suited for a map of the globe if you're just looking at the state of California, for example. So picking a projection, projections are identified by CRS codes. You can use epsg.io to identify the EPSG number. You want the appropriate projection, as I was saying, for your area before you start your data analysis. And you want to check the initial CRS code and transform to a different projection if you need to. So that was a lot. Do we have any questions before we switch over to Python?
Haven't seen anything coming through in the chat yet, but y'all feel free to use the chat if you do have any questions. Thanks for stopping and asking, Jonathan.
Okay, I'll keep going. Thanks, Rachel. So aerial and polygon data. So we refer to features measured on spatial areas and polygons as aerial data. Sometimes these will come in shapefiles. So this is a file format that contains an area boundary, so data describing the boundary, and measures for each area. You'll see these often have a .shp extension. And sometimes we'll work with polygon data that comes in a CSV, sometimes a GeoJSON, .geoJSON, which is a geospatial JSON object. And often we'll have a column that has a unique area identifier that we can use to merge the data into an existing shapefile with boundary info. So we'll explore this when we go over to the Python script, but this is really important. This is how we link these different types of data sets. So we'll be using I won't get ahead of myself. We'll get there. But these linkages between the data sets are really important, as you might imagine. So we need to ensure that we have a unique identifier to go from data set 1 to data set 2. A data example, Rachel so kindly downloaded and cleaned data on melanoma, skin cancer incidence in California, in the counties in California, from the U.S. National Cancer Institute's state cancer profile databases. There should be a file named CA County Melanoma in the folder. Let us know if you don't see that. And we're going to import this into Python, link it with county boundaries, and map the incidence rates of melanoma in California. So I will switch to the Python script. Let me see how to do this. Okay, so can you see Google Collaboratory and some Python?
Yes.
Okay, lovely. So let us know in the chat if you have trouble with this. When you go to the folder, you should be able to open this Python notebook. When you say open with, there's this app, Google Collaboratory. It's a way of using Python in your browser without having to do anything locally in your machine. If you don't see this, you can go to Connect More Apps and you can search for Collaboratory. And if you don't see that, let us know. I had to install Collaboratory yesterday for my Google Drive. So I thought it came standard, and it clearly does not. So let us know if you can't find that. We're going to open that. I have mine open here, and get started doing this geospatial analysis. So not seeing anything in the chat. The first thing we're going to want to do is install relevant packages. So you can run that first cell. And actually, so that we're all working together, I'm going to delete these files, or we're going to actually leave those because it's going to take some time, but we're going to import the files from the folder. So CA County Melanoma, and then also eventually this UV index.tiff, and this US County zip from the Census Bureau into our script. So once you've run the first bash script to get the packages, we're going to import everything we need. And hopefully that should work if you've imported what you need. And then we're going to load this melanoma data from the CSV. So if you haven't used Collaboratory before and you're following along, what you're going to want to do here is get the CSV from this Google Drive folder into the Collaboratory. So I would download this here onto my local machine, and then go back to Collaboratory, and then I would say upload, and I would upload this CSV here. I already had it preloaded, so I don't actually need that. I'll delete that. But hopefully that should work. And then we're going to be able to read it from this file explorer. And something to note about Collaboratory, files are downloaded after your runtime disconnects. So you can use them while you've connected to a Python runtime. This little indication up here at the top right shows you that you're connected. You're using an instance to run this notebook. Once that disconnects, you will lose the file. So make sure that you're downloading anything from here. If you produce a data set that you want to keep, you download it out of Google Collaboratory onto your local machine, or you put it on Google Drive. So we're going to load this melanoma data from CSV. And so I'm going to run this, and then I'm going to see what the data looks like. And we have this FIPS code. So this is a 5-digit county identifier. First 2 digits, 06, is the state code. And then the last 3 are the county within the state. And this is that key to linking the data sets that we're going to use. FIPS code is really great for merging data in the US. It's a unique identifier that we can use to get from dataset 1 to dataset 2. And then we have this melanoma rate per 100,000. And this is pretty self-explanatory. It's the county melanoma rates per 100,000 people in that county. So now we're going to get our geoboundaries data. And so I downloaded this TL 2024 US county.zip, this folder from the Census Bureau. And you're going to want to ensure that it's that you're uploading it here into your runtime instance. And then we're using GeoPandas, which is a Python library that we use to process and visualize spatial data. If you've ever used or heard of the Pandas library, this is very similar. Pandas is a Python library for working with data. GeoPandas is a analogous Python library for working with spatial data that uses a lot of the same functions. So that's really convenient. So we're going to load in this file, and then all we need here is California. So we're going to filter it to just California using that state FP code. And then the other thing we're going to do here is we were talking about projections. So we're going to use this California specific projection EPSG 3310. And then we'll plot this. And so GeoPandas allows really easy plotting. So we've read in these county geoboundaries, we filtered it, and then we're just plotting it. So this is a geodata frame, and you can just say plot the geodata frame, and we'll see that looks like the state of California. So we have the state and then the Channel Islands. Looks pretty good. We can see these county boundaries. That's wonderful. So we have this geographic data. Now we want to merge it with the melanoma data. So next we'll merge in the geoboundaries file. We have this GeoID tag. In melanoma, we have FIPS. If you remember up here, we're using FIPS to denote the same code. GeoID in the geoboundaries file denotes the same. So we're going to merge that, and we can see what does that look like. Okay, wonderful. So we have a lot of information here. The Census Bureau provides a bunch, some that we will use, some we don't need. So we see the state FP code, the county FP code, and then the names, and then a whole bunch of other variables, including the area of land and water, which is really interesting. We have this geometry right here. And then on the far right, we see the data from the data set, the melanoma data set that we loaded in and that we merged. So the FIPS code and the melanoma rate. We're going to see there are a couple counties where we don't have a melanoma rate, but for most of them we do, and this looks great. So now we can map this, and so we can plot this using, again, a native function of GeoPandas, and we're just going to plot a simple chart of or visualization of the melanoma rate per 100,000 in California. And look at that. So this is wonderful. We have converted this data by county into a map that we can use to see, wow, interesting. It looks like down here on the coast and also here, we have quite high incidences of melanoma. And in some of the other places throughout the state, we're missing a couple here and here and here. And it's an interesting patchwork. So that's wonderful. It would be really great if we could use our pointer to sort of zoom in and see what the data are showing here. And there are great libraries to do that. So we're going to use one called Folium, so we can zoom and explore the data. And so we're going to use a slightly different projection. And then this code right here, we're making a chloropleth map, which is using color to denote different measures of the melanoma rate. And we're using Folium to make a map that is both embeddable and also is explorable. So I'm going to run this. Hopefully, if you're following along, this has worked so far, and this cell works as well. We'll see. Wonderful. All right. So if you're following along, hopefully now you can mouse over and see the name of the county, the rate of melanoma per 100,000. You can zoom in. We're using a backing map, so you can actually see where these geoboundaries sit in the state, and you can explore this data, which is exciting. So with that, do we have any questions?
Thanks, Jonathan. The only thing I'm seeing in the chat is some folks are getting errors with the Plotly, installing the Plotly package. But I can try to help troubleshoot that in the chat rather
Oh,
than doing that live.
interesting.
I was not able to reproduce that error. It's installing okay on my end.
Interesting. Jacob, good question. I would try Googling that and seeing if Googling it with saying trying to install Plotly in Google Collaboratory and then with the error and see if that's a common thing. That I haven't actually seen that. Oh, you're using Jupyter Notebook. Okay.
Oh, okay.
Um, all right. Well, shapefile boundary wasn't loading on your computer.
So I think you would need to download the shapefile from the Google Drive. If I was understanding right, you need to download it from the Google Drive onto your local machine and then upload it into the files in the collab session.
That's right. Yeah, it's a multi-step process. I can go over that again in the interest of time. So we're going to do this again with raster data. I'm going to go back to the presentation and we can go through raster data, and then we'll go back to the Python script.
Some folks are saying it just takes a bit of time for the
Yeah.
shapefile to load. Sorry about that. So we do have a question from Luciana saying, if we didn't have a column called FIPS, but we have a shapefile of the US and the health data with the polygon and specs of each county, how could we merge it? It's a good question.
Yeah, that's a great question. So there are ways that are slightly that can be slightly harder to use, harder to go with. If you have, say, the name of the county and the state, you can sort of map that to the FIPS code. So you can each state has, as we walked through, the state FIPS code, and then the county, which together produce the GID or FIPS that we've been using. So you could map backwards with that. Restarting the kernel. Thanks everybody for troubleshooting this live.
Yeah.
It can be a little bit a little finicky sometimes. Okay, in the interest of time, I'm
We got,
gonna go
for those
back.
who were having trouble with the shapefile, it looks like we got a suggestion to modify the file path to match where you save the shapefile. The original code has the contents folder, which should be removed. So for some folks, that could be causing your problem with accessing the shapefile that you upload. Thanks for submitting that
Yeah,
suggestion.
thanks for that. Okay, so we're gonna move on to importing, processing, and mapping raster data in Python. And we'll go back to the Python notebook and keep working through this and troubleshooting once we've talked through some raster data. So what is raster data? We talked about it as a grid of pixels or cells. You can think of these as rows and columns. So a single band raster is the simplest, which stores the value of a single variable in each cell. So if you think about that, the projections of future heat stress in Australia, that was a single band raster. You can also have multi-band rasters, which store a number of variables, or one single variable that's measured at different instances of time for each cell. So we can see we see a whole bunch of different type of file extensions for rasters. There's TIFF, spelled two different ways: .nc, .bil, .ase, .img, and .jpeg. So a raster data example. We grabbed monthly average UV index for California from the NASA Earth Observatory's data set. These are in the uvindex.tiff raster file in the Google Drive. And this should say Python. We will show how to import these data into Python and map them. So let me actually pause here, go back to the script. Okay. Back to this Python notebook. We're going to want to download again the UV index.tiff. So I'm going to download that locally. It's much smaller than the county geoboundary. So hopefully this is pretty simple and quick and easy. And then we'll upload that here into our runtime instance. And once you've done that, we can read it, and we're using this raster.io library for reading it in. And so now that we have that, we can take that raster data and use the geometries of the area that we're interested in. So in this case, it's the state of California, to mask the raster. I realize this is skipping ahead a little bit. So essentially what we're doing is trying to take, it's like kind of like cookie cuttering. We're cutting out the cookie of California from the raster, using the geoboundaries that we grabbed earlier from the Census Bureau. And so we only want the ones that are within the area of interest. So in this case, it's all the counties in California. So we're going to use this transform function to mask it, to do that cookie cuttering. And then we're going to show what that looks like. So we can just run this whole thing and get this lovely picture of the UV index masked to California. And so you see it's a grid of cells with discrete values that show the UV index throughout the state. So let me know if that works, if you're able to reproduce that figure, if you were able to download and then upload and then load in the UV index data. Great. Okay. Luciana, it worked. Awesome. Wonderful. Worked for Lauren.
Yeah.
Great.
Looks like it's working great.
Okay. Awesome. So we will go back to the presentation. All right, my Zoom's being weird. Are we seeing linking raster and aerial data?
Yeah.
Lovely. Okay. So now we get to do the fun part and link these together. So we often in climate epidemiology align the rasterized climate exposure data with the health outcome data, the aerial health outcome data. So to do this, we usually compute a weighted average of the values of the climate variable across the raster cells that intersect with each polygon. So here we may want to compute a weighted average UV level across grid cells within each county, and then link that county level UV with melanoma rate data. So we'll walk through this. That's a bit of a mouthful. We're going to go back to the Python script and link these. All right. So how do we aggregate the raster data to the county level? One of the simplest approaches is to compute the average UV across the grid cells if the centroids fall within each county's boundary. So to do this, we can use this zonal statistics library in Python, which is lovely for computing these types of values. And here, let's actually do this piece by piece. So we're computing the zonal statistics. What is that? What's going on here? So let's actually make that prettier. Oh, that's a list. Okay, so we are going to calculate the zonal statistics for each county. Then we want to extract the mean UV index. And so we use this code here to do that. And then we're going to add the mean UV index as a new column of the geodata frame that we've been working with. So we're taking the computed statistics and adding them into the geodata frame, and then and showing that that updated geodata frame here. So we're here grabbing, if you remember, we got a bunch of columns that are interesting, but we didn't need for this analysis from the Census Bureau. So here we're grabbing the columns that we need, and we have this GeoID or FIPS code, the name, and then the melanoma rate and the mean UV index, which is wonderful. So now in one data frame, in one geodata frame, we have what we need to do this analysis. So we can map the mean UV index by county. So let's do that. So now we've taken that raster of the UV index, and we have aggregated those values to each county using the polygons from the Census Bureau. And we can show by county what the mean UV index is throughout the state of California. And so we're rolling here. Okay, Alina, if we had multiple years of annual incidents, like 2020 to 2025, we wanted an average of the period over each region. Got up till now. Okay.
Thanks for the good question about should you do first temporal, then spatial, or first spatial, then temporal? That's a really good question. My sense is that it shouldn't matter unless you're doing some kind of weighted averaging, or if somehow your boundaries change over time. If your boundaries are changing over time, then it may matter. But if you just have static area boundaries, then I think you should be okay to do either one. I don't have a strong preference. I would guess in most cases they'll give something quite similar. I don't know if you have any other feeling on that, Jonathan.
That sounds right to me. Thanks for that, Rachel. That was a great question. Okay, it looks like we're following along. Wonderful. Okay, we can ignore this because I was writing this to a GeoJSON. So, and then I was also writing it to a CSV. So we have this mean UV index in California. We also have computed both. We've built both a folium map that we can explore and also this static map of melanoma rate per 100,000. And so we can link them together. We can show them side by side. Here we're plotting them both side by side, and using the work that we've done up to this point. So hopefully you were able to follow along on this, and we're doing great on time. So we're gonna get to explore some Flourish Um, I want to make sure everyone, if you have any questions, throw those in the chat. Um, or we could even take some time now and if you want to ask questions directly, if you have any. But I'm glad that for some of you, you're able to get through this.
Yeah, and if at this point folks do want to unmute themselves and ask questions, I think we can allow you to do that. Have to figure out how, but just shoot us a message in the chat if you do want to ask something, and we'll be happy to unmute you and let you talk directly.
Yeah. I'll stop my share for now in case anyone has a question.
Oh, yeah, and Elaine says to raise your hand. That sounds like a much better system. I didn't know if that was possible. Thanks, Elaine.
Yeah,
Sorry, it took me a while to find the unmute button. Can you hear me okay?
I can.
Oh,
Hi.
thanks, Jonathan. Yeah, so I'm primarily R user and I really use like TGS or the tidy census package to like call some command and I don't have to, save a shapefile locally and then upload them for mapping. So I'm wondering, you showed an example of you can have a shapefile locally uploaded and use it for mapping, but is there a similar functionality of like interacting with the census API or just call another package to get that shapefile instead of going through this like file upload step?
Yeah, great question. Thanks for that. So R does have great functionality for this. Python has a couple libraries where you can do something similar. I wanted to show this version of downloading the geoboundaries and then uploading it. It's clunky, but it's a way of for more for US applications, there are various libraries. Thanks, Rachel. There are packages that you can use to interact with the US Census geoboundaries and make that are very analogous to that R functionality. But if you're doing something, a calculation, or if you're working with data that are not where there is not such a Python package, you might have to do this version of interacting with the geoboundaries. And so I wanted to show some love to our federal data and download that and use it directly from the census site, and then also show how you could do this if you were working with geoboundaries for a country that, say, doesn't have a Python library where you can easily grab those boundaries and interact with the census API, for example. That was a great question. Thank you.
Thanks.
I think through Google Earth Engine, which we've done a previous tutorial from Cafe on scraping data from Google Earth Engine using Python. I believe through Google Earth Engine, you can get a lot of administrative boundaries, shape files for kind of the whole globe. I can try to dig some of those up while you continue talking, Jonathan.
Thanks for that. Google Earth Engine is great. And in geospatial, there are a whole bunch of really wonderful resources. and lots of folks have there are a bunch of great tutorials both from Cafe University and then out there on the web for how to work with different administrative boundaries and different types of data. And there are a number of folks who are devoted to trying to make it easier and more accessible to work with different types of geoboundaries and at different administrative levels from granular to very broad all across the globe. So it's a great community of folks dedicated to this. Thanks, Rachel. Okay, wonderful. Well, if there are any more questions right now, and we have about half an hour left, a little bit more, I figure we can switch gears and use a no-code tool. So Python is wonderful. I use it all the time, but sometimes you just want to drop something in a visualization software and not have to do some of the same work to process and visualize by writing code. And for that, we're going to use Flourish today. And so this is going to be a bit of an experiment. We'll see how this goes. If you've never used Flourish before, it's a great software that has a free tier, and you can use it to do a whole bunch of different types of data visualizations. So if you go to that link, you should be able to say get started now. And you may have to create an account if you want to follow along with this. And we're going to experiment with just dropping in some spatial data. And so we are going to give air quality statistics a try. Oh, thanks so much, Rachel. And so I'll share my screen again. We're going to go to this website. And so say I'm exploring different types of data. I'm interested in air quality. I want to use it for a project I'm working on. And I'm not quite sure what types of data might be useful to me. I find this EPA, air quality cities and counties data, and just want to do some exploratory data analysis. So I could do that in Python and follow some of the same steps that we just did. But I'm pressed for time, and so I'll use Flourish, and I'll give this a try in Flourish. So I'm going to download this air quality statistics by county. So it comes up with this link. And then I'll go over to Flourish. And so I'm already logged in. If you may have to give this make a quick account and then log in. And then I'll go to new visualization. And just to give Flourish a quick shout out here, they've done a bunch of work bringing functionality to some of the most common and most exciting types of visualizations. So a bunch of different line, bar, and pie charts, projection maps that we've just been talking about, and we'll use one of these, scatter, 3D maps, which are really interesting, pictograms, marker maps, bar chart race. These are interactive visualizations that show changes over time. You've maybe seen visualizations like this, looking at, for example, what country has the biggest GDP over time by year, and you'll see countries shift places and race in the visualization, Sankey diagrams, cards, network graphs. So they are working all the time to bring great no-code tools to all of us, and are adding new types of visualizations. So this EPA data is cities and counties in the US. And so what I'm going to do here is use a projection map for the United States. So let's see, US counties diverging. So I'm going to use US counties here. And when I open this up, they load some preview data, and let's see. Okay, so we've got population here already. We've got counties. As you see, this is interactive, and they use a projection and a visualization of the United States here, where we have the lower 48, we have Alaska, Hawaii, and then we have Puerto Rico, which is part of the United States, and is often left off of maps. So this is great. We can see this, we can see what it looks like, and then we can go into the back end and see where this data is coming from. Wonderful. So we have regions and regions geometry. So this is the data that Flourish provides us. If you click on this geometry data, you can see the same, this is polygon data, and you can see the coordinates that are used to make this polygon on the map, which is really cool. And you can see a preview of what the polygon looks like. So I'm going to upload some data. Say upload, and then where is that? City Factbook 2023 from EPA. Great. Okay, air quality statistics by county. So what do we have here? So this is sort of an exploration now of what this data set consists of. We could have opened it locally, but Flourish is also allows us to see what this looks like, and it's sort of like an Excel analog in how we can visualize it in the table. So we're seeing state, county FIPS code, great, population, and then all of these measures of air quality. So we have PM10 and PM2.5 particulate matter measures at different time scales. So let's take a pause here. We have all these different measures. We have this data set, but let's see if they have a data dictionary, because it would be great to, they might not, that might be shame. So it would be wonderful if we had, let's see. All right, so they have descriptions of what these columns are, it looks like, here on the website in these trends. So we're seeing CO, lead, NO2, O3, PM10, PM2.5, SO2. So they are here. There's a bit of a data dictionary. What I'm looking for here is, to back up a step, is we have this data set, which is great. We want to understand where the data is coming from, how it was made, how it was collected, and what the methodology is there. Because we don't want to be using data that we don't know the provenance of, we don't know how it was collected and shared and disseminated. So it's good to see that there are these pages where we can see sort of a description of a few of these measures. So all the ones that are in that data set. How are we doing on time? Okay, good. So that's good to see. So now we know what some of these columns represent. And sorry, Luciana. the link to download the data. Of course. Wow, sorry. That was. Here's the link to download the data. I grabbed the air quality statistics by county. Oh, and I should have mentioned, this is also, I put it in the folder. So CTY Factbook 2023 in the folder. So you should have access to it. And if not, you can download it from that link that I just shared. And it's pretty small, so hopefully it should download okay. So we found this data. We know more or less what the different values are. And so we can go back to Flourish and see what we can do with it. So we have the state, the county. We care about this FIPS code. And so when we go back to this region's geometry, we saw this county FIPS column E. We want to link column E IDs to match. They have it all set out for us. IDs to match county E or column E, sorry, with regions here with the county FIPS code. So ID, they've already, Flourish is pretty smart. When you ingest data, they identified that this would probably be the ID column that we want to map. They already pulled out that column for us. Name, let's see, name that appears in pop-ups and panels. We actually probably don't want the state. We want the county. So I'll say column B. So we're using the county name. And then color by. So there's population, but we're actually trying to visualize air pollution here. So we could use one of these other measures. And we could pick any of them. We could also label by one of them. So what you'll see is this data is kind of sparse. We don't have data for every county, for every measure. And so we could use one of these that seems to have more data. Ozone 03 seems good. We can color by I here, and we can also label. We'll just color by that. And if we preview it, so we're seeing quite a lot. This is kind of chaotic. What's happening here? So we still have the Flourish population data showing. That's points here. They preloaded some of the state populations. So we can actually, if we don't want this to show on the map, we can just get rid of it. Go back to the map. Okay, a little bit less chaotic. Now we're actually seeing a value on the map for 03. We're seeing county pop-ups. It would be great if we could see the measurement too. So let's go back to the data in the regions, and we could use info for pop-ups. Let's see if we can do it with label. Oh, sorry. Live demos. Okay, so we're coloring by 03. Info for pop-ups. We can add custom pop-ups. That might be a little bit more than we want to do right now. We can also add additional measures to show when. So potentially we could do this. We could color by 03, but then we could also show other measurements of PM10, PM2.5, for example. So taking a step back, we have this map. We have a bunch of missing data, but we have a map that's showing some interesting information across the US. And just to put on some best practices on this map, we can add a quick title, and we can add some labels so that someone knows, if someone sees this, they know what we're trying to show here and how we use this data. It's also really important, of course, to cite where we got our sources. And so we could, here on the right, Flourish adds all of these controls. And so we can, let's see, go to the header and add a title and a subtitle and add text. We also want to make sure that we are adding the source. And so I could go back and grab the URL from where we grabbed the data. And Flourish will link to it. So if we clicked on that, it will take us back to that data page. I'll add a title. See. So yeah, it's O3. We're visualizing O3 8-hour ppm. So we don't have to get too complicated, but just to give some context here to someone who approaches this. And so in 10 minutes or so, probably, we took some data. We were able to sort of get a sense of how it was, what the values being communicated are, and then also just drop it straight into Flourish here and come up with a visualization. This isn't super complete. We would want to add quite a bit more. We would probably want to play with how we can visualize the other measures, so PM 2.5, the other air quality measures that are in the data set. But this is a pretty good starting point. It's a powerful tool to spin up really quickly a visualization of spatial data. And as we saw scrolling through the options, Flourish offers a bunch of different ways of visualizing data, including some three-dimensional maps. And so that's something we could play with another time, or I'd encourage you all to explore on your own. That's a way of using spatial data and trying to, again, there will be some distortions and some weirdness, but trying to visualize it in a potentially more natural way using a globe, using 3 dimensions. So I will stop there and see if there are any questions. And feel free to raise your hand or drop something in the chat. I hope you were able to follow along. That was a bit ad hoc there at the end with Flourish. I can't possibly have answered every question that you might have. But hearing none, I think actually we might be able to end a bit early. Oh, I see a question. Okay. Favorite data visualization template in Flourish? Ooh, great question. There's so many. And my colleague Zach, I think, is on this call, and he's a Flourish wizard. So I'd be curious if he has any thoughts too. I've used Flourish for a number of things. And one of the reasons to use Flourish and Data Wrapper, both these no-code tools, is that they provide a really easy embeddable object that someone can, well, this is one of the pluses. Someone can take that and put it on a website, or you can host your own site, or just embed something on the web and let someone play with data. So I used it back long ago, to, let me see if I can find these. To show the increasing burden of dengue in a changing climate. If you look at this story down at, so we have a couple of visualizations. I did some work with some colleagues with the Rockefeller Foundation. And oh, thanks so much, Elaine, for sharing that out. If you scroll down, I'll share my screen just to make sure in case that doesn't work. So this is a story that we wrote about how dengue is, the burden of dengue is increasing due to climate change. We talked through why that is, and then visualized some measures of this explosion, as we called it, of dengue. Here we see that bar chart race template. So it's interactive. You see this dramatic increase of dengue cases over time from 1990 to 2019. So a truly stunning amount of cases by year, and as effective. I'm not going to call my own visualization good. A hopefully effective visualization of how dramatically dengue is rising around the world. And then here we had a spatial visualization of the reports of dengue in tropical and subtropical zones to try to communicate that we're seeing it. We are seeing dengue cases crop up in places that once had were dengue free, or there was very little chance of seeing dengue cases. We're now here in the United States seeing dengue in Florida and Arizona, in California. Oftentimes, we have seen dengue brought back to places like I'm calling in today from Boston. Travelers will go to a place that has endemic dengue or has quite a bit of dengue, then bring it back. We're actually starting to see some local transmission in the United States and in other zones that have historically not been sent as dengue. So these are two visualizations I made that I tried to use to communicate this this really pressing global health problem. And Flourish was wonderful for that because we were able to work with data and clean it and then drop it in Flourish, and then give that embeddable object to the web team at the Rockefeller Foundation, who could just drop it into the story. So Flourish was great for that. Okay. Any other questions? We have some time and I'm happy to just hang out if anyone wants to chat visualizations.
That's so cool. A really great example of how powerful data visualization can be. Thanks for sharing that, Jonathan. I love that.
Thank you. And if we don't have any question, oh, difference between Flourish and Data Wrapper. Great question. For those of you who haven't used it before, I'll drop the link to Data Wrapper. Let's see. There we go. Data Wrapper is another no-code tool for data visualization. It was developed actually for newsrooms, and so you'll often see Data Wrapper visualizations used by media. They're known for being very simple and clean and effective. The goal is to try to not be too busy and just communicate very clearly particular types of data. They don't really have support for spatial data, so I was ambitious. I was like, we're going to try to use Data Wrapper to communicate spatial data. They're not as great as they haven't added as many templates for data visualization as Flourish has. So wonderful for bar charts and scatter plots and creating these embeddable interactive visualizations, but not so good for the spatial data visualization that we're talking about today.
Jonathan, would you mind chatting a little more about like the challenges of making embeddable objects in Python or coding-based languages? You sort of mentioned that a couple of times as something that's an advantage of these point and click no-code tools. Is it hard to do in Python or our other coding languages?
Great question. So it takes a little bit more effort than just outputting this, essentially drag and drop object like with Flourish and Data Wrapper. But that Folium map that we made, that actually we can output as an HTML and then open that up and interact with it with a browser. And we can create embeddable plots that are interactive. One of my favorite libraries for data visualization in Python that has a slightly higher learning curve, or slightly steeper learning curve, I should say, but is really, really powerful and that has incredible documentation, is Altair. And this is declarative visualization. There's wonderful support and user guides. And if you're interested in diving into data visualization, I'd highly recommend Altair. And they have good walkthroughs for how you can create something that is easy to drag and drop into a web page, and not just produce a static visualization, but produce an object that someone can interact with and click on.
This is really cool. I didn't know about this. This looks awesome. I'm going to play around with it. Thanks.
Sure.
If no other questions, we're almost at time. So thanks so much, Jonathan. This has been really fantastic. I learned so much, as always, from you. And I want to encourage everybody before you hop off to stay in touch with us and keep up. We have a lot of webinars coming up in the next few months. So please keep an eye on our newsletter and calendars to learn about those. And thanks for joining today.
Thanks so much, everybody.
Thanks.